Hello family, this is our overview for Units 2 and 3. So Unit 2 was kind of weird because it was just those baby tabs in our notebook. So the baby tabs were on like locations in a set of data. But not only that, so if we go to the baby tabs, you can see that from chapter 1 we talked about standard deviation. So standard deviation tells you how far on average your observations are from the mean. So we're focusing on the variation around the mean. Then we went into z-scores because z-scores is how you express an observation in terms of standard deviations. So standard deviation is the variation around the mean or oftentimes around the center of your data. Z-scores tell you how many standard deviations away an observation is from the mean. Then we talked about the normal distribution, and the idea of a normal distribution is based around this idea of 1, 2, and 3 standard deviations around the mean is where most of your data is. So we talk about standard deviation, we talk about how to express observations in terms of standard deviation, and then we talk about this distribution that is based off of standard deviations. And within this is the empirical rule, which says 68% of your data is within 1 standard deviation, 95% is within 2, and 99.7 is within 3. So on your overview, you can see this empirical rule here. Then the last thing that we went into in this unit is percentiles, and your AP classroom defines percentiles as the percent of data values less than or equal to a given value. So if we're talking or asking about, well, what percentile is your test score in, what you would find is how many people scored lower than you, essentially. So these 4 baby tabs are actually very important. It is extremely important that you understand standard deviation, that you truly understand what a z-score is, that you understand the empirical rule, and that this is the empirical rule. These pictures describe the empirical rule. And then percentiles is important because they're almost guaranteed going to ask you to find a mean, a standard deviation, or a value of x based off of a percentile. So it is not by accident that each one of those sections has their own little tab because they're super important. And then all of that leads us into the standard normal curve. And it may seem weird, but our first lesson in the standard normal curve is transforming data. And then we actually talk about changing observations to their z-score so that we can find probabilities on a standard normal curve. So the more you understand about how these ideas relate, the better off you will be for your exam coming up. So I've tried to make some connections on this overview for us. So the first part of this overview is talking about transforming a data set. And these visuals are just a quick reminder that if you multiply or divide, every value in your data set changes. And the reason why it changes is because multiplying takes your data set and spreads it out. So all values get bigger, including standard deviation. If you divide an entire data set, by a number, it shrinks it down and becomes less wide. So multiplying spreads it out, dividing smushes it back up. Because of that, it changes every statistic. So remember, statistics are things like the mean, the standard deviation, the 5-number summary, your IQR, and your range. Remember, a statistic can be any of these things, which relates to confidence intervals and sampling distributions and hypothesis tests. We can do those things for all of these kinds of statistics. Then the second picture is showing you that multiply, just kidding, add and subtract does not change spread. It does not affect how spread out your data is, because when you add, it just takes this entire data set and moves it up. And when you subtract, it will take an entire data set and just move it or shift it down. It's not going to change the width of your data. So it's not going to spread your data out or smush it back up. All it does is pick up this entire data set and shift it. So spread doesn't change. Well, how does that translate to most of the problems that you're going to get? Well, this problem at the very bottom is a perfect illustration of this. So they're telling you you're going to transform a data set, and what you're going to do is you're going to add 0.1 to the old pH level, and then you're going to multiply all that by 1.2. So if we correct the mean, we do only, oh, this is backward. Oh, no, it's not. So when we correct the mu, we do everything. We add on the 0.1, and then we multiply by the 1.2, and we get 5.64. But when you correct sigma, you only multiply by 1.2. You do not add or subtract. Why? Because sigma talks about spread, and adding and subtracting does not affect spread. So when you calculate your new value, you do not add or subtract. You can see that here. We added 5 to this entire data set, but standard deviation, IQR, range, they did not change because spread doesn't change. But up here, when we multiplied, spread did change. So that's the first really important topic from this overview. Then, after we talk about transforming data, I have standard deviation. And I'm sure you guys are thinking, what? How do we go from transforming data to talking about the spread of data? Well, stick with me. Standard deviation is the variation around the mean. Remember, standard deviation is not resistant to skew or outliers, because standard deviation takes into consideration every single data value. So if you have an outlier, it's going to increase your standard deviation. This is a small standard deviation. This is a large standard deviation, because standard deviation measures the typical distance of values from the mean. So the flagpole would be your mean, and in this case it's also your center. So we're talking about, on average, how far away are the points from the center. This is giving you an idea of standard deviation in terms of a normal curve. And you can see as the standard deviation gets smaller, the normal curve gets taller and skinnier. As the standard deviation gets bigger, you can see that our standard normal curve flattens out and gets a lot wider. So, then this red bar in the middle is illustrating this question. If the standard deviation of a set of observations is 0, you can conclude that all the observations are the same value. If there's more than one observation and there's no spread, there's no standard deviation, that means that every single value is the same. How do we interpret standard deviation? You must always use context. You cannot just say 4 typically varies about the mean by about 2. You have to add in context. So here, always use context. You want to say the height typically varies by about ½ an inch from a mean height of 5 inches. So always use context, always include units. And then this was a really common problem that we saw in this unit. If you have a set of data with a given mean and standard deviation, what happens if you add in a point or take out a point? So in this case, your mean is 81, these are test scores, and your standard deviation is 9. So on average, scores are about 9 points away from the mean of 81. If one student was absent on the test day and his score was 81, what would this do to the mean and the standard deviation? Well, the new score equals the mean, so the mean would stay the same. The standard deviation, well, we want to look at how far away from the mean is our new observation. Well, it is the mean, so it's 0 away. That does not mean that standard deviation stays the same, though, because your current standard deviation is 9. So if we add in a point that has a standard deviation of 0, your standard deviation will decrease. Those are the basics, the foundation of what you need to know about standard deviation. So, transforming data, biggest takeaways are multiplying and dividing changes every statistic. Adding and subtracting does not affect spread. Then we go into the standard deviation idea that talks about variation around the mean. So how do these two things connect? These two things connect when we're talking about z-scores. You can standardize any data value by finding its z-score. So you take the observation, subtract the mean of the data set divided by the spread. What does this tell you? Standard deviation, just kidding. A z-score tells you how many standard deviations from the mean and observation falls, and in what direction. So if Jenny has a z-score of 0.99, that means that Jenny's score is 0.99 standard deviations above the mean score of 86. We would not be able to find z-scores. We would not be able to find z-scores if we were not able to transform data. So the reason that these two are connected and together is because transforming data allows us to find z-score. And that's what this little arrow says. Transforming data allows us to do z-score. Well, how is z-score related to the next section? Z-score is how you can take any normally distributed data set and use the standard normal curve to find probabilities. So I'm going to say that one more time, and it's extremely important that you understand this. Transforming data allows us to find z-scores for every observation in the data set. Why are z-scores important? Because z-scores allow us to take any distribution that is normal or approximately normal and use the very specific standard normal curve to find precise probabilities or percents or proportions. So, on the very top of this last section, you have the normal distribution. We have the normal distribution. So this is empirical rule. Your mu would be in the middle, and then you have 1, 2, 3 standard deviations coming out of that. The most important thing to know about a normal curve is that mu and sigma can be any value. Any value. So down here, we're comparing two normal distributions. Notice on the normal distribution, mu and sigma can be any value. On the standard normal distribution, mu can only be 0 and sigma can only be 1. This is what allows you to find all of those probabilities, percents, proportions, areas, however they like to call it. So you can take any normal distribution, convert the z-score, that's what this is, it's a formula, and use standard normal, your purple table, to find probabilities. That's what it's saying under here. Remember, standard normal table always tells you the area to the left. Finding the area under the curve, you must use a z-table. And then this is just walking you through how you would find the area for a proportion or z-score, find the area to the right. So I just want to move these just a smidge so you can see what I wrote next to those arrows. Okay, then on the back side of this, my zoom out button is broken on my document viewer, and it seriously gets my rageometer going so bad because I have to press the zoom out like 78,000 times. So on the back of my, on the back of this overview, I wrote a reminder to myself of how to find all of these areas under a normal curve. So an area to the left, an area to the right, an area in the middle, and an area on the outsides. I just wrote symbols. I did not give any specific values. If this is something you struggle with, you're going to want to get into this section in your notebook and actually write down specific values on this overview. So do that, please. The other thing that I wanted to make sure that we know has to do with how we actually use a normal distribution. So in some cases, you will be given mu, sigma, and x. The distribution has mean mu and standard deviation theta. What is the probability, proportion, or percent of x? So this is just generic how they can set up a problem. So in your review, you have a few of these. I will try to find one very quickly. I just don't want to waste your time by looking through this. So in the free response, you have one here. So your Chevy Malibus have a mean of 18.7 miles and a standard deviation of 4.3. What is the percent of vehicles that have worse gas mileage than the Malibu? So you want to make sure that you know this is your mu, this is your sigma, this is your x. So you go through and you use mu, sigma, and x to find your z-score. Then you go to the table, the purple table, to find z. So for a normal curve, the most common thing that you see is take mu, sigma, and x, use it to find the z, then find the area under the curve. So in that particular problem, the final answer is that I'm sorry, I'm wasting your time. About 7%, no, even less than that, less than 1% of all vehicles have worse gas mileage than the Malibu. So the percentage for that problem I just looked at was really, really small. The other thing that you will likely see is related to this, but they give you the percent first. So if they ever say to you, the percentile is this, what is the top 10%? What is the bottom 5%? There's a problem in your review that asks about if you get rid of the lowest 10% of something, what is the smallest value you would have? That's this kind of a problem. So they give you area under a curve and want you to find Z. So you have to look up inside the purple table for the decimal that's closest to this area. They give you an area, you find the Z by looking inside the table. Then they're going to ask you to find one of these things based off of that Z value. So they could ask you to find X or mu or sigma. This has been very common in your multiple choice, I feel like, and this is on that problem in your review. What is the X in order to fall within the top 10% of all cars? So you need to look up the Z-score that matches 0.10 inside the table, and then use that Z-score to solve for X. So that is review page 11. So this entire part of the back side of my overview, you can see an example of each on page 11. So if you need a concrete example, you can find it there. The back of my overview looks like this because I've added in the things that I needed to remind myself of. The front of my overview has the things that I showed you. Remember that these are all related. Transforming data allows us to find Z-scores, and Z-scores allow us to use the standard normal curve. The background information we need to have there is that adding does not change spread, subtracting does not change spread, multiplying and dividing though does and changes everything. Standard deviation is your typical variation around the mean, and for a regular normal curve, mu and theta can be any value, and the data is distributed according to the empirical rule, which is 68, 95, 99.7. Any questions you're going to want to ask me? Please, I want you all to be successful on this exam. I know that this is a lot of work, but it's going to be worth it. Okay, that's it. Love you guys.